is we're going to look at example 2.3. Okay, so I'm going to use this process to visualize how to solve this problem. Okay, so what it says here is that you are driving down the highway late one night at 20 meters a second when a deer steps onto the road 35 meters in front of you. Your reaction time before stepping on the brakes is half a second, and the maximum deceleration of your car is 10 meters per second squared. A, draw a motion diagram and plot position, velocity, and acceleration for the car. And then how much distance is between the deer and the car when you come to rest? So let's go look at this thing. Okay, so I'm going to dissect this carefully. So here I go. So here's my solution now. So when I look at the solution for this example, I want to rely on my graphs or my motion diagram to understand the situation. Sometimes a graph is better than a motion diagram. There are people who prefer graphs over motion diagrams. In some shape or form, you got to figure out what works best for you. So the first thing I want to do here is that I want to visualize. So A here, what I want to do here is that I want to visualize the overview picture of the motion. Let's do that now. So the first thing that we're seeing here is it's saying what? You're driving down the highway at 20 meters a second. Note that there's no speeding up or slowing down. You're moving at constant velocity. When a deer steps into the road 35 meters in front of you, your reaction time before stepping on the brakes is half a second. So what does that mean? Your reaction time. That means you are moving at constant velocity. So when I say reaction, what that means here is that there is zero acceleration and moving at V1 at a constant rate of 20 meters a second. So let's look at that. So what do I know about that? So in this interval here, I'm going to pick just some particular point, and it's already been established that my motion here is then going to look something like this here. So I'm moving at 20 meters a second here. And I continue to move at 20 meters a second for this interval here. And what I know here is my acceleration in this first interval is 0. And then what happens here, and so this is what maybe I should draw this, you know what, I'm going to move this over a little bit. Okay, in fact, I'm going to move it down. And what I'm seeing here is this right here. This point here is where you see the deer. So it takes you a moment to realize that you need to apply the brake. So during this time, you are continuing to move at the same speed because all of my intervals are the same distance. All of my intervals are the same distance. So when I now what I'm going to do here at this point right here, I'm going to apply the brakes now. So it takes time for you to move your foot off the accelerator pedal onto the brake. Once you do that, now I have an acceleration that's going to be in the opposite direction. That acceleration, we now know, tells us that I have a maximum deceleration of 10 meters a second. We know we're slowing down. So then this value here becomes minus 10 meters per second every 1 second. So what is this region right here? You can see here is that this region is my reaction region. This right here is my braking region. So as I continue to move in this direction, what am I going to see here? Well, I'm going to have to change how I look at my, you know what? I'm going to move these down because I want to add another variable right here. Okay. So now what happens? Look at my squares. I have 1, 2, 3 squares. So now I have to go to a smaller distance. Look at my distance now. So in fact, what I'm going to do here is that I'm going to change colors to signify that I'm now in a different region here. So now this is V1, has the same speed, but now look at this interval. It's smaller. So therefore, my arrow has to be smaller here, right? I'm getting smaller. Instead of 3 squares, it's 2 squares. And then I'm going to continue to reduce this because you could see here that this is getting smaller. And so then I'm going to say that this is now like this. And then at some point, I'm going to say here that this is where I stop. Okay. So if I stop right here, that's going to be my final velocity right there. Again, look at my intervals. They're getting smaller and smaller. So from here to here, you could see here is that this is why this is my braking region right there. So now, what do I know? What I know about this is that we know that this car, during the reaction period, travels this distance, which I'll call delta x1. And then this car, the car here travels this distance from here to here, which I'll call delta x2. The only thing we know about this motion here is that this is the total distance. So the total distance the car travels is then going to be delta x1 plus delta x2. And because of the wording of this thing, we don't hit the deer because they're asking us for the distance between the deer and the car. So somewhere over here at this point is where the deer is located. That's what our picture is telling us right here. So I can now draw a motion plot for this situation. So the first thing that I typically do here is that I'm going to look at my velocity curve, and then I'm going to go for my acceleration. So what do I know about my velocity? My velocity continues for a speed something like this here. This is my speed V1. that speed is 20 meters per second. What's my acceleration at this time? Well, I'm moving at constant velocity, so I can see here that this acceleration 1 is 0 when I look at this guy. But now, what happens? I have negative acceleration. That negative acceleration is going to bring the car to a rest. So that means I have to come all the way down to here because I know at this point, this thing is 0. So the only way I can change that is if my acceleration at this point, which is minus 10 meters per second, is it minus 10 meters? I forgot. I think they said it was minus 10 meters per second, is every 1 second. So you can see here is that when I'm looking at my intervals, I really have 2 intervals right here. There's my green interval here, where I'm moving at constant velocity. And then you could see that I'm changing my velocity right there. So this guy here is my velocity curve. And you could see here is that what I'm going to do here is that this very bottom here, I'm going to call that V2. Because those are the only 2 velocities that we have. And if I come in here and I just lightly plot the position curve, what do we know about the position curve? The position curve essentially says this, that the car is moving at a constant velocity. What do we mean by a constant velocity? That means that this guy is a linear line like this. And then what happens? The car then, the slope has to start to decrease. And when the slope is 0 right there, right, you could see that all of these are together right here. And what you're seeing here is that when I get to the very, 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 very top, note that the slope is flat there, which tells me that V equal to 0 is that. And so this distance between here and here, you could see that this distance here is delta x1. This distance here is delta x2. So now I'm going to say that this is how I'm trying to visualize the motion. So now what I want to do here is that the question then comes down to this. How much distance is between the deer and the car when we come to rest? So in other words, what we're really asking is, what is the total distance that the car travels? And then that tells me here is that the total distance of the car should then be delta x1 plus delta x2. Then the second question is, what is the distance between the deer and the car? So in this case, we're going to have some difference between the two, and it should be the distance that the deer is at minus the distance of the car. So you could see that everything that we really got to figure out is the distance that the car travels. So here I go. So if I look at my motion diagram, which I'm going to bring down here with me, you could see here is that the motion diagram or plot shows two intervals, which implies I have to apply the kinematic process 2 times. Not 1 time, 2 times. So here we go. So what I'm going to do here is that I'm going to focus just on this first motion right here. So what I'm going to do here is that I'm going to get rid of this thing right here. Okay? I do not care about anything else. I only care about the first part of the motion. Okay, so now that I have that, what do I know happens here? So when I look at this motion, I'm looking at this thing and I'm saying, so what do I know? Well, I know that my reaction time, which I'm going to define as T1, is going to be 0.5 seconds. So here I go. So now I'm going to determine delta x1 first. So I set up a data table. So if I set up a data table, that means that for this interval, I need these things here. So note, I am adjusting my values as I go along. Because this is my interval right here, probably going to need more space. Then what I'm going to do here is that what is it that I do know about it? Well, one thing that really sticks out is that I clearly have that the acceleration is what? It's clearly 0. The other thing that's really clear here is that my time here is half a second. Now let's look at my initial and final velocity here. Now note, I wrote this as V1, and I also wrote this guy right here as V1 as well. So note that the initial and final speed of this interval, which in this case, I'm going to just change this lightly. This is V0, but V0 is the same as V1. So this tells me immediately that I'm going to have 20 meters per second here, and I'm going to have 20 meters per second here. So note, I have all of the 4 variables. So the one quantity that I'm looking for is this distance, delta x1. So what do? I go to the kinematics table. Let me go grab this table right here and bring it down. So if I bring this down, what you're seeing here is that here's my kinematics table. So now what I'm going to do here is that I'm going to use this kinematics table to pick out the right equation. So because we have all the unknown variables, of course, besides x1, we can use any equation that has delta x. Okay? So I can't use the first one. It doesn't have delta x. So I can't use this guy. So that's out. Look at this guy. Look at the second equation. So if I look at the second equation here, this one gives me, so look at how I'm writing my notation. This is going to be V1 squared v initial squared plus 2a delta x1 and a1. Note, because I have acceleration equal to 0, this equation tells me that v1 and v initial are the same. We already knew that. That doesn't give me any new information. So therefore, this equation does not work because it's giving me no new information. It's not giving me anything about delta x. So now let's look at the second equation. If I look at the second equation, then I'm looking at this guy and it reads delta x1 is equal to v initial t plus 1/2 a1 t1 squared. So when I look at this thing, I go like, hey, I can use this equation. Again, when I look at my acceleration, this guy is 0. This immediately tells me that this is the equation that I should be using right here. So I can use this equation right here. So if I look at this, then the kinematics table shows to use delta x1 is equal to v initial t. And remember, that other term is 0. So now I can mathematically put in my numbers. From the table, you could see I'm going to write 20 meters per second. And then my time here is going to be 0.5 seconds. So that's going to give me 10 meters. In other words, my distance, delta x1, is 10 meters. So I have now solved for my first distance in here. So now what I want to do is that I want to go determine delta x2. Well, let's go determine delta x2. So what I'm going to do here is I'm going to go back to my motion diagram. Okay, here's my motion diagram right here. And now I'm looking at the braking process. Okay, so I'm going to clean this up a little bit. So here's what we know. So I'm going to look at this guy, and I need to solve for delta x2. So now what I'm going to do here is I did before. Look what I did before. I set up a data table. From the data table, I then use the kinematics table to pick the right equation. So now let's set up a data table. So if I set up a data table, now look how I'm changing my variables now. I'm going to go delta x2. My acceleration is different now. And then I'm going to have v2, v1, and then my interval t2. So now I'm going to go from my picture and I'm going to pick what I know. Clearly, we have to solve for x delta 2. That's what we were trying to shoot for. So now, look at V1. I know what V1 is. We know that V1 was 20 meters per second. Look at V2. It stops, the car stops, so we know that this is 0. What about the acceleration? We know that the acceleration in this case is minus 10 meters per second every 1 second. So the one thing that's not given here is what? The time. So it's the time that tells us which equation to use. So instead of looking at what you have and then trying to find the equation by picking all the right variables for that equation, I'm saying go to the one that you don't have. So here I go. Now let's look at the kinematics table. So if I bring my kinematics table here, man, I gotta apparently, let me go down here. So now I'm gonna use the kinematics table to pick the correct equation. So when I look at this thing, here I go. Here's my kinematics table. I'm only looking for the time that we don't know. So I go to the time, look at my time. This is the only location that says I don't have the time. So that means I have no choice but to use this equation right there. No choice. Right? So that's my equation. So now, to solve for
Good
delta
morning.
x2, was that a question? To solve for delta x2, we use, now again, putting it into my notation here, it's going to be v2 squared equals v1 squared plus 2a1 delta x, oops, that should have been a 2. So now, look at my kinematics equations. Velocity 2 is 0, right? This guy is 0. So now I can mathematically solve for delta x2 now. So what I'm going to do here is that, look what I'm going to do. I'm going to take v2 or v1 squared to the other side. Okay, so if I take this to the other side, mathematically here, I'm then going to have 2a2 delta x2. I'm going to get minus v1 squared. Now, what I'm going to do next here is that I'm going to divide both sides by 2a2. So if I divide both sides by 2a2,
oh good, and you took the sign down.
then this is going to give me, I'm going to isolate, I'm going to get delta x2, and I'm going to get minus v1 squared over 2a2. So now,
Might just see the word canceled and turn around.
So now I can now plug in these values right here. So if I plug in these values, you can see here is that V1, we already said that that was 20 meters per second. Note that the acceleration is negative, which is 10 meters per second every 1 second. So if I now plug in these values, what do I have? I have minus, and then I'm going to get 20 meter, this guy squared, and then I'm going to get meter squared, second squared, divided by 2. Look at the minus sign. I'm going to put the minus sign out here. So then this will be 10 meters per second every 1 second. So right away, you can see that this guy and that guy cancel each other out. And if I get this numerical value, I punch this into my calculator, I'm going to get that this is 30 meters for delta x2.
Can you please mute Paul, Carlos?
You know, this, I am really trying. How do you mute?
I think you go to his box and you hit the 3 dots in the corner. I think as the host, you have the potential to mute him, if I'm not mistaken.
So we went to go see Terminator last night.
For like the original Herman?
1980.
Hey, Paul, stop talking.
It was playing somewhere?
At the Scotts Valley one.
Damn it, I don't see it. They changed the format of this thing.
Okay.
I'm so sorry.
Which is gonna be right around Halloween. I don't think I'm ready to watch The Shining still. Watch it as like a 5-year-old.
I'm sorry. I don't,
It's really scary.
I'm not seeing where to mute everybody. Ah, okay, so now what I'll do here is that I now know the total distance of the car. So the total distance of the car is then delta x car, which will be delta x1 plus delta x2. We saw that this was 10, this is 30, so the total distance is 40 meters. No. Do I have a mistake here? How far is the deer away? That's 440. Oh, dude, this is 20. My numbers are wrong because I have hitting the deer. So this is 20 and this is 30. Oh, okay. So now I know what the total distance that the car travels. So then they tell us that the distance between the deer and the car now between the deer and car is then going to be this delta x will then be the distance of the deer minus the distance of the car, which will be 35 minus 30. So you stop 5 meters in front of the deer.